Welcome back to EE 210B. We are going to continue our discussions of inference over networks, and today I will be talking about combination policies, right? We have talked multiple times about combination policies during this course. Today I will talk a little bit more, and in particular show you how do you adapt the combination policies, okay? That's the purpose of this lecture, okay? And it's based on chapter 14 from the reference that you have listed over there, okay? So if you recall, okay, the performance expression that we derived in the previous lectures very much depends on A through its dependence on the Perron entries, right? Okay, so here it is. I have the expression on the next page, right? This is the mean square deviation, and then you have a similar expression for the excess risk, right? So the performance depends not only on the Hessian matrices of the cost functions and on the covariance matrices of the gradient noise process, but it also depends on the topology through its dependence on these P's, right? So this is the performance, and you have a similar expression for the excess risk. And then the next question becomes, how do I optimize the selection of A or the selection of P's in order to minimize the MSD? We solved this problem, right? 2 lectures ago, or last lecture, I believe, we solved this problem and came up, for example, with the Hastings rule. That's one solution to this problem, okay? However, if we recall, the Hastings rule depended on certain parameters theta that depended on an SNR measure in the network, right? Which requires that you know how much noise you have in your network, how much signal power you have in your network. And very often this information is not available beforehand. You need to estimate it. So we'll be talking about this later in this lecture, okay? Even though we know one optimal A, it doesn't necessarily mean that we know how to construct it, okay? Very good. So I know that the performance depends on A. So how do I pick A? Okay, so let me first talk about static choices for A. So if you look into the literature, okay, you are going to see that there are many choices for A that have been proposed in the literature for various reasons. We have already talked about several of them. The metropolis rule, the uniform rule, where I give weights to my neighbors, right, in proportion to the number of neighbors that I have, right? That's the uniform rule. If I have 3 neighbors, each one gets 1/3 or 1/4, counting me. The metropolis rule, right? You have a degree, I have a degree. The degree is the number of neighbors we have. That's the NK here. This is the degree of agent K, how many neighbors agent K has. In the metropolis rule, if he's my neighbor, how much weight I'm going to assign to the link between us. I'm going to find out his NL, my NK, 1 over the maximum of these 2 numbers becomes our weight, right? That's the metropolis rule. Okay, so let me show you several other choices of rules that are available in the literature. So, and this is my notation. This is the degree for agent K, right? So the size of its neighborhood, which includes agent K, and max is the maximum degree across the network, right? So here in this sorry, not yet. And in the table, you are also going to see the Laplacian matrix, which, by the way, we saw earlier in an earlier lecture what the Laplacian matrix of a network is, right? You know, the combination matrix. We also talked about the Laplacian matrix. If you remember, it was defined like this. Across the diagonal, okay, it has the degree of the agent minus 1, right? If you take the 3 entry of that matrix, it will be the degree of agent 3 minus 1, okay? So here it is, okay? So this is L, okay? So if K is equal to L, so on these diagonal elements here, you are going to have the degree of that agent minus 1. And in the off-diagonal elements, you are going to have minus 1 if the agents happen to be neighbors, right? That's how you build the Laplacian matrix, okay? And if you remember, the Laplacian matrix has several useful properties which we showed. For example, it's always a non-negative definite matrix. If you go back, there is a lecture where we covered the properties of the Laplacian matrix in some detail. I'm just reminding you here of the results, okay? The entries on each row, okay, add up to, I think add up to 0. Maybe there is a typo here. Add up to 0, right? Because you have, let's say, you have 4 neighbors, so this will be 3, and then you will have 3 minus 1s on that row, right? So this is just a typo, okay? And then the smallest eigenvalue of this matrix, right? It's non-negative. Its eigenvalues are 0 and non-negative, right? Are non-negative. The smallest eigenvalue is 0, and how many times that eigenvalue is repeated, it tells you how many disconnected subnetworks you have, right? So if the smallest eigenvalue has multiplicity 1, then you know that the network is connected, right? This was one useful property of the Laplacian matrix, okay? Very good. So I only mentioned it here because it will appear in this table. So what you have in this table are examples of static combination policies. By static, I mean they are fixed. They depend only on the topology. They do not depend on data. They do not change with time, okay? So for example, can you read this slide, or is it too difficult? For example, the very first one is the uniform rule, right? 1 over the number of neighbors. If you are my neighbor, 1 over the number of 1 over my degree, otherwise it is 0, right? What you have down here is the metropolis rule, which we use many times, right? 1 over the maximum of nk and L. Down here you have a rule that we proposed in 58, where if he's my neighbor, I'm going to assign a weight that's proportional to the relative degree. His degree relative to the amount of degrees I have in the neighborhood, okay? There are reasons for that, but this is one rule, okay? And these are more general rules, okay, defined in terms of the Laplacian matrix. So here you see, I can define A to be 1 minus some beta times the LK entry of the Laplacian matrix. Why is that? Special cases of this give you matrices that we have seen. For example, here, if you set beta equals to 1 over the maximum degree, right? 1 over the maximum degree. This is very much like almost a uniform rule. You assign 1 over the maximum degree from across the network to your neighbors, and then you adjust AKK such that they all add up to 1, right? If I have nk degree, if I have nk neighbors, each one of them I'm assigning 1 over n max. So nk minus 1 times 1 over n max is how much I assign to all of you. 1 minus that is how much I need to assign to myself, right? That's the idea, okay? If you choose beta equals 1 over n, you get this other rule, okay? Also called sorry, I think this is the maximum. I'm confused if this name should go there instead, but anyway, you get the idea, right? Okay. Special choices for beta give you these combination policies, okay? Now, and in the last column, I'm telling you whether the resulting A is left stochastic or doubly stochastic and so forth, okay? So we have seen a few of those. Now, these are all useful matrices, right? And they have been proposed for different reasons. But in the context of adaptation and learning, one thing that you observe is that these coefficients are fully dependent on the network topology, right? They just depend on how many neighbors you have or I have, right? They don't depend on data statistics, right? They do not change with time. They only depend on the topology. In the context of adaptation and learning, that's not enough. We can do better if we use different A's. For example, we showed you 2 lectures ago that if you use the Hastings rule, you can optimize the MSD. You get the best MSD possible. But if you look at the expression for the Hastings rule, the A's are not dependent only on the topology. They also depend on how much noise power you have in your system, for example, right? Which is data dependent now. Okay, so these are examples of static policies, and like I'm saying, they are essentially determined by the topology, right? By how much connectivity you have in your network, okay? But in the context of adaptation and learning, we need to have more flexibility in selecting these combination coefficients, okay? So I already showed you before one example, again, the Hastings rule. If you remember, okay, it is coming up. I'm going to list it. The Hastings rule was defined in terms of a certain parameter theta squared, just because it's non-negative, we defined it as theta squared. And whether you are dealing with the MSD performance or the excess risk performance, the theta was defined like that. Either the trace of the gradient noise power, Rs, or the trace of the gradient noise power, G, multiplied by H inverse, which is a measure of signal power, the Hessian matrix, right? So this is more or less like noise over signal power, right? The inverse SNR, okay? So the Hastings rule, which was obtained by minimizing the MSD performance measure, was defined in terms of these parameters theta, right? Let me see if I have the expression coming up. Well, it's coming up much later, it looks like, okay? But if you remember the, okay, I used these thetas to construct optimal Perron entries, right? For example, 1 over theta k squared, and they are normalized, right, to add up to 1. Remember? I use these thetas to construct the p's, and then I use those p's to give you an A, right? To give you an A that has this P as the Perron eigenvector, right? That's how I constructed the Hastings matrix. It will come up. The expression will come up, okay? I'm just reminding you, okay? But still, if I want to use that matrix, I still need to know these thetas, and they depend on, for example, in the quadratic case, in the mean square error case, when H is RU, I still need to know that RU, right? I have D's and U's. I have measurements, right? D's and U's. But I may not know the RU, okay? And this G will depend on sigma V squared times RU. So it has RU in it again, and it has sigma V squared in it again, right? So you need to know the signal power and the noise power to find the theta. Okay, so that's one problem which we are going to resolve later, okay? Very good. Okay, so that's why we need the policies to be adaptive. We need them to learn the theta. And adaptive because this noise power may change with time, right? Okay, so the RU also may change with time. If that happens, if you have a policy that's learning theta adaptively, it will be able to adapt to changes in the statistics of the data, okay? So that's why we need these policies to be adaptive, okay? So let me show you an example first before I discuss how do you do that, okay? So this is an example in the context of mean square error networks, okay? So you have a collection of n agents. Each one of them is receiving, right, data at agent k that satisfies this linear regression model, and the unknown is omega 0 across all agents, fine? And the noise power at agent k is sigma v squared, and I'm assuming here that the step sizes are uniform across the agents, and the signal power is uniform across the agents, fine? This is just a simple mean square error problem, okay? So in this case, if I write down what the Hastings rule is, okay, we did this before, right? This is what it turns out to be, the Hastings rule. The RU, because it's uniform, will cancel out from the expression for theta, from the numerator, okay, and the denominator, okay? But now, to use this expression minimizes the MSD, will give me a network that will be able to learn with the best MSD, right? But I need to know the noise power at the agents, right? So that's one problem there. So I need to know how to learn the noise power, okay? This is just to show you what's happening, okay? So this is one example of an optimal rule, Hastings rule, okay? Now, in this particular rule, okay, by the way, this is fully distributed, right? Somebody asked me this question last time, and you already see it here. The Hastings rule is fully distributed. I'm agent K. I only need to know the degrees and the noise powers of my immediate neighbor L. I don't need to know anything beyond my neighborhood, right? So the Hastings rule is distributed, okay? Number one. Number two, you might say, okay, another thing that you might say is, well, but these expressions for P depend on this normalization. This normalization is constant for everybody. It's just a scaling constant, right? Okay, this theta k squared is only at agent k, okay? Anyway, but for the A, what you need here, the degrees and the noise variances you have. Now, in this particular rule, in the Hastings rule, I only need to assign a weight to our interaction. I only need to know information about you and about me. Right? That's one aspect of this rule. There is another rule that I'm going to describe later. Okay. Now, if you remember, how did we derive the Hastings rule? The Hastings rule was derived under a certain condition, a certain restriction. I assume that the Hessian matrix is uniform across all agents. If you remember, this was a restriction I imposed in order to simplify the optimization problem and then solve it. We assume that the Hessian matrix H sub k is uniform, equal to H across all agents. That led to the Hastings rule. Okay. Later in this lecture, I'm going to derive another rule, okay, another rule for you, okay, that does not require this restriction, okay, that does not impose this restriction, okay, and it leads to a policy that looks like this, okay. I'm going to show you this. I haven't shown you that, okay? I'm going to go back to the MSD expression, optimize it, but without that condition, or optimize an approximation to it without that condition, okay? That's what we will do. When I do that, I will arrive at a different choice for A, and this is the choice. So the degrees are not there anymore, okay? So to assign the weight to our interaction, I just need to know his noise power relative to the neighborhood noise power. Right? And this is intuitive. So you see, the smaller his noise, the bigger the weight I'm going to give him. Right? That's what this is saying. Okay? So this is another rule. Okay? Another rule that, but still, in this rule, I still also need to know what the noise power is. So regardless of which rule you want to use, the previous rule, the Hastings rule, which optimizes the MSD. By the way, which MSD the Hastings rule optimizes? It optimizes the first order approximation of the MSD, right? The MSD expression that we optimized was the approximation for the actual MSD to first order in mu, correct? In mu max, right? Okay, so I take that first order approximation, impose that the Hessian matrices are uniform across the network, I get the Hastings rule. The second rule, which I call the relative variance, okay, rule, relative variance rule, okay. For this second rule, I'm going to use to work with a more general expression for the MSD, the one that is more general. We talked about it before. I'm going to show it to you very soon, then you will remember, okay? Because there was another form of writing the MSD in terms of a series, okay? And that series was a better approximation for the MSD expression than the one we used, okay? So I'm going to use this more general form without imposing the constraint of uniform Hessian matrices and arrive at this other expression, okay? Very good. So now, so I haven't derived this, I'm just showing you the result, okay? So for example, let's assume, okay, that I'm applying the ATC diffusion strategy here to estimate the WO. If your A is static, this is what you are going to use here. If your A is not static, right, if you want to use this A or the previous A, right, you still have to estimate the sigma, correct? If I can estimate the sigma, then that estimate I can plug it here and end up with an estimate for this A, right? Correct? Okay. In that case, I will replace this by an A that is changing with time. Correct? So this is what I have here. I'm going to show you later that one way to estimate the noise variance would be to run a recursion like this. Okay? What is this recursion? I am node K. He sends me, because remember, I'm doing diffusion, right? Each agent adapts its weight and then shares that intermediate estimate for the combination step. This is what I have, this is what you shared with me. I'm going to compare them, okay? That energy I'm going to show you later, provides an indication of how much noise he has, okay? This is what we are going to show, okay? So if I smooth that energy over time, this is just a filter, right? The first order IIR filter, okay? First order IIR filter, that is a small number. Okay, I'm just smoothing that energy over time. Okay, I'm going to show you that this quantity here over time is going to converge to a value that's proportional to the sigma that you want. It's not exactly the sigma that you want, but the quantities around it are constant. So when you put it in the numerator, you put it in the denominator, they disappear. So you only end up with the sigma, right? So this quantity here after sufficient time has elapsed, right, this quantity here, after sufficient time has elapsed, is proportional to the sigma v L that you want, correct? So you can use it in your expression for the A here. You can replace these sigmas by that gamma, correct? That's the idea, okay? Of course, I have to justify all of this. This is coming, okay? But that's where we are going, okay? Very good. So let's now start the theory of this, okay? I will derive it not for MSE networks, but more generally, right? Broader networks, okay? So I'm talking now about noise-aware policies, not static policies, right? So these are adaptive policies now. If you know the noise, you can put them into the expression. If not, you have to learn them, okay? So one noise-aware policy that you already know about is the Hastings rule. We derived it before, right? To derive the Hastings rule, I assumed that the Hessian matrices were uniform across the agents. Remember that? Okay. And then I formulated a problem like this. The MSD expression under that condition reduced to a form like this. Find the P's, right, in order to minimize the sum of the trace, subject to the condition that those P's will be the entries of the Perron eigenvector, right, of the resulting matrix A, and they add up to one and they are positive, right? Meaning I have a network, I already have the topology, I just want to find the A, right? I want to find the A. And the A that I want to find is such that the P that corresponds to it minimizes this expression. This way I end up with the smallest MSD, right? This was the problem we solved before. And the solution was given by this expression, right? Depends on the thetas. Again, this is distributed, okay? This is distributed because you only need the thetas of your neighbor, okay? Fine so far? So this is the Hastings rule. We already saw it, okay? It is noise aware because it depends on quantities that depend on the noise, okay? So how do I estimate the thetas? So this is one thing I'm going to answer later, okay? Now, let me show you the second rule, okay? The relative variance rule. How do we get that rule, okay? Now recall that to get the MSD, to get the Hastings rule, I worked with this MSD expression, right? This MSD expression is an approximation for the actual MSD up to first order in mu, right? This expression here is of the order of mu. Higher order terms in mu, we ignore them, correct? Okay? But then if you go back to the lectures, those were the demanding lectures when we were deriving MSD expressions, right? One of those lectures, we derived, I showed you other forms, other ways for writing the MSD, okay? One was a more general way, and if you remember, on that particular general expression, I applied a low-rank approximation, which led me to this result, okay? So I'm going back now. I want to start from that more general expression. The more general expression was this one. This is one form of it. There is another form. This is one form in terms of a series expression, okay? Now, I'm doing the analysis here for ATC, but similar results will hold for CTA or consensus, okay? So this is a similar expression, a more general expression for the MSD, okay? 1 over the number of nodes. H is 1 or 2, it doesn't really matter, okay? And then you have, so it's a series, right? Trace of by b star. And these quantities depend on the dynamics, right? Which I'm going to list on the next page. But what I want to emphasize is that if I take this expression, okay, I can simplify it, and I did this calculation before, and you get the previous first order expression, okay? Very good. If I take this expression here, this expression will include a term which first order in mu, plus higher order terms, little o, higher order terms in mu. If I throw this term here will be exactly that expression, okay? Very good. So what are the B and the Y? Here it is, the B. This is for ATC. It depends on the combination policy, on the step size matrix, on the Hessian matrices, and the Y. And this S here contains information about the noise covariances, okay? Now I can formulate the problem in this domain. I can say let's find the A, the left stochastic A that minimizes this MSD expression, right? Just like I formulated it using the first order approximation, I can formulate it using this more general expression, right? Of course, this is a more difficult problem to solve now, right? Because you see, A appears inside B, and then there is a power here. A appears inside this B, and then there is a power. So this is a more complex expression, right? It's much more difficult to solve. You see here, B has A, Y has A twice, right? And then you have powers of B as well, and then you are adding an infinite number of terms. So this is not a trivial optimization problem if you want to solve it like this, okay? So we don't solve the optimal problem. This is what we do instead, okay? Okay. So this is the problem that I would like ideally to solve, okay? Minimize that MSD, subject to what constraint? I would like this F as this A to be left stochastic. Its entry is non-negative, right? Okay, so the topology I'm given, I would like you to find the left stochastic A to solve this problem. Again, this is a difficult problem, non-trivial problem to solve, okay? And this is what I'm going to do next is not uncommon in engineering. If you have a very difficult optimization problem like this, one way to go around it, right, is if I can bound this cost, and then I minimize the upper bound, okay? Of course, you are not solving the original problem, but you are trying to get as close as possible, okay? So find an A that minimizes the upper bound. At least I will know that whatever MSD I get there will be an upper bound for this. And if that is small enough, it's good enough for me. That's the argument, right? Okay. Now, you can show, and I'm not showing it here, there is a reference, I give you a reference in the text, okay? In one of my articles, you can find the entire proof for this. That this sum that you have on the left-hand side, okay? Let me see if I have the reference here. Here it is, okay? If you go to this article, this is the chapter survey, okay? If you look into that section, you will find that, that relation, okay? You can show that this series is upper bounded by some constant that's independent of A, and that's critical. C has to be independent of A, otherwise, right, times the trace of Y, the trace of what's here in the middle, okay? So this is my first remark, okay? So C is independent of A, okay? So here it is. So now I'm going to minimize the upper bound, minimize the trace of Y, okay? Now, what was Y? Remember, Y, okay? Here it is. A transpose M times M. Now, M times M times S times A, right? So the trace of this, okay? The trace of this Y, okay? You can express it like this, okay? You can show, okay, that the trace of Y can be written like this. You have just to do the algebra, expand that product. You are going to find, right, the trace is the sum of the diagonal entries, right? That the trace of Y is this double sum of the products of the step sizes, the entries of A, the trace of the GLs. These are the individual noise covariances, okay? You see there is no H now anymore. The Hastings rule, that's why I don't need to impose a condition on H, because the H does not appear. Okay, the H used to be inside B, and B disappears once you bound it, okay? So that's why the H is not a problem anymore, okay? I would like to minimize the sum over what? Over the entries of A, okay? You see, this is, so I can split this into n separate optimization problems, one for each row of A, okay? One for each row of A, okay? Because they are not coupled. Okay, so here it is. So for example, let me minimize this sum, okay, for each row, for each k, fixed k, let's minimize this sum, okay? This will give me the entries, sorry, for each column of A, right? For each column of A, okay? So let's fix k, minimize this sum. That sum will only depend on the entries on that column of A. It doesn't depend on the entries on any other column of A. That's why I can decouple that problem into n separate optimization problems. Understood? Okay. The A's have to add up to 1, non-negative, right? These are the usual conditions. Now, this is a trivial problem now to solve. Why? Because this is quadratic in A. You see, if I take these little A's, collect them into a row vector or a column vector, take the trace of G, collect them into a diagonal matrix, you will get an inner product like that, A transpose gamma A. Sorry, take the mu times the trace of G, collect them into a diagonal matrix gamma, right? And then collect these A's into a column A, and then row. So this becomes minimizing a quadratic cost, right? Subject to a linear constraint on the A's. Right? This is similar to the Hastings problem we solved. You can use, for example, Lagrange multipliers to solve it. It's not difficult to solve in this case, okay? So if you do that, you get a very similar expression to what we got last time. Because last time we minimized a similar expression over the P's. Okay, I don't know what notation I used before, but I had something like this, subject to the condition that the P's added up to 1. This is the vector of 1s. Right? Here you have something similar, subject to the condition that these A's add up to 1 also, right? And non-negative. So you get the same results. Here it is. Okay, where in terms of these gammas here. Okay, so the diagonal entries of that matrix gamma, I called it little gamma here, gamma squared, right? So each gamma here is the trace of the covariance GL scaled by mu. Okay, so these little gammas, they determine the A. This is the relative variance rule that I showed you before. Okay, this is for the general case. This is not for the mean square error case. This is for the general case. Okay, understood? Okay, so this doesn't have a condition on H, but this optimizes an upper bound on the MSD. Okay, and it is, we call it relative variance just because it is a relative measure here. Okay, this is a variance like a noise variance related to a noise variance or the inverse of that. Okay, very good. So let's go back to the example. Fine, so now you understand Hastings rule and the relative variance rule. These are two rules that are noise aware. Okay, they are not adaptive yet. So let's go back to the mean square error example. Uniform step size, uniform covariance. The G in this case is given by this quantity. Okay, so what is the gamma? I define the gamma to be mu L squared, mu squared trace of GL, correct? So in this case, this will be mu squared, because mu is constant, trace of GL. So it will be sigma V squared 2 times trace of RU, correct? 2 times trace of RU. And this trace of RU and mu squared and the 2 will cancel from up and down, right? And you get exactly what I showed you earlier in this lecture, right? The relative variance rule depending only on the sigma V squared for the MSC problem. Now, what if I don't have a uniform RU? What if RU changes with K? What if the step size changes with K? It doesn't matter. Your gamma now will depend on mu L, will depend on RU, right? What will happen? This will continue to depend on, sorry, I'm writing here gamma L. So this should have been L here, right? So the only thing that will change is that these quantities now will depend on L, right? And you just plug them in. Okay, so that's what I'm doing next. Okay, so for example, you end up getting this general expression down here, where the mu's and the r's do not disappear, but they are there, right? Okay, but the important thing is that what you need is to estimate this gamma. Once you estimate the gamma, if you know these things, that's it. If not, you have to estimate the gamma. Understood? So we have seen 2 examples of noise-aware policies. I'm not saying these are the only ones, but these are 2 examples that we formulated based on solving a well-defined optimization problem, right? Okay. So now let's take this a step further. If you know the thetas, if you know the gammas, you know these policies, but in general, you don't know that, okay? Okay, very good. So remember, we are trying to solve over the network a problem like this, right? Optimize an aggregate cost function, right? Now, for the remainder of this lecture, I'm going to assume that all the G's here, the J's, have the same minimum, omega 0. So that the global cost has also the same minimum. Why is that? Okay. Because if that's not the case, your network will instead be minimizing this aggregate cost, right, weighted by the Q's, remember? And your network will instead be tending to the Pareto solution, which is the minimum of this, the W star. That W star depends on Q, right? Different A's will give you different P's and therefore different Q's and therefore different W stars, okay? Since now I'm in the business of adapting the A's, by adapting the A's will be changing, the P's will be changing, the Q's will be changing, W star will be changing, right? So it becomes difficult to do the analysis in this case, right? And, okay, so that's why I'm going to assume that all these J's have the same minimum, right? Which is common in many cases of interest, quadratic costs, right? In machine learning, that's not uncommon, right? So let's assume the JKs have the same minimum. This way, the omega naught will not change with A changing, okay? So I can measure how close I'm getting relative to that omega naught, okay? Very good. Okay, so here I'm just reminding you what the Pareto solution is. And since the individual costs have a common minimizer, omega 0 and omega star will be the same, okay? And this is a useful condition because A now is going to be changing in an adaptive manner. So if that's the case, then omega 0 will be insensitive to that, right? Okay, very good. So let's again talk about ATC. You can repeat the analysis for, the conclusions will hold, right? Similar conclusions for CTA and for consensus, okay? So this is my problem now. I have a distributed strategy running over my network. And this is the general case, okay? What I would like to do is this. I already know what's the best A I can use here. Hastings or relative variance. But these depend on thetas and gammas that I don't know, because they depend on noise variances that I don't know. So the question now is, how do I estimate these quantities so that I can find what ALK of I should be here, right? And then I end up adapting A as well. So I end up with a strategy that involves multiple adaptation layers, right? This is the traditional layer plus one for adapting the A's. This is where we are going for, okay? 2. So this is what I would like to show first, okay? I would like to prove this lemma first, which is, remember, because I'm dealing with the general complex case, I always extend the quantities. Otherwise, you don't have to worry about the E's, right? Just work with in the normal domain. You don't need to extend, okay? So what I'm going to show is, remember, this gamma is the quantity that I want, right? It is the proportional to the, it is the quantity that I need in the relative variance construction for A, right? Okay. So I'm going to show the following. If I'm agent L, I can compare my existing estimate to my updated estimate, right? This is after you do the adaptation step. I can compare that variance, the size of that error, and I'm going to show you that the size of that error tells me what this gamma is up to second order in mu. So this term is a small, higher order in mu, this mu squared. This term is a small, so for all practical purposes, this difference at node L is what I want. And now, the question is, I don't have this variance at node L, but I have these I have realizations of these two quantities, right? So what you can do, you can run a smoothing filter at that node L. A smoothing filter is running, like I showed you before, that is averaging, saving these values, right, over time. Right? You could save several of these values over time and just compute the average of this squared quantity. Or you can just smooth it in real time, as I'm going to show you. But first, let me prove this result, and then I'm going to show you how you implement it, okay? Okay, so now, first is the proof of this result. Okay. Now remember, again, these are things we saw many times in this course, okay? Using the mean value theorem, right? I can take this extended gradient vector here, right? Extended gradient vector, and express it in terms of a Hessian matrix right, times the extended error vector. This is just direct application of the mean value theorem, okay? You have seen it many times. If you just go to the statement of the theorem, this is exactly that. What is this? This is the W minus WO extended, right? Okay, and this matrix we usually call it H. This is what we call H at node L, okay? Very good, okay? Even though I'm using W star here, but because I'm assuming all of them have the same minimum, it's WO, okay? There is a typo in the notes, right? The error is the error, right? The tilde is missing, okay? Very good. But now, you see, if you go back to the algorithm, I'm interested in this difference, correct? I'm interested in how close these are to each other, right? The variance. But that difference is mu times the approximate gradient, correct? What is the approximate gradient by definition? It is the true gradient plus the gradient noise, right? Okay, so I'm going to write this difference is squared is mu times the true gradient plus the gradient noise is squared, right? So that's where this expression that you see on this page here came from. You see that difference is squared. I'm writing it for node L, right? That difference is squared is the step size is squared, and you see here the gradient noise plus the true gradient. And because I'm dealing with complex data, they are all extended. That's all, okay? So, okay. There's a typo there, right? Do you see it? Yeah, you know, once you start writing these terms so many times, it's easy to get confused, right? So this should be SL E, correct? And SL E star. You get the point, right? Okay. It's hidden there, but it is there, okay? Now, okay. What else? Well, this true gradient, I just used the mean value theorem to show it is H times W tilde, right? So far, so good, nothing, okay? Now, expand this. This is a quadratic term, right? So you'll have the step size is squared times the square of this, and then the cross terms, correct? So there it is. The square of this, the square of the second term, minus, because you have a minus here, 2 times the real part of the product of both terms, right? 1 times the other, correct? Right? This is just linear algebra, okay. Now let's bound each one of these terms, because what is it that I want to show? I want to show that under expectation, this whole thing becomes gamma L squared plus something small in mu squared, correct? Okay. Now, we showed earlier, so now, under expectation, right, if you put expectation here, you will get expectation here, expectation here, expectation here, correct? We showed earlier that, what about this first expectation here? We proved in an earlier lemma, right, if you go back to these results, that that expectation is the trace of the gradient noise of SL plus a power of mu. This result we proved exactly the way you have it there, okay? Fine? Okay. And we also proved, and here it is, expression 9107, that the second term that I have, under expectation, it is of the order of mu squared. We also proved that result, okay? We proved that under expectation, this quantity is of the order of the 4th power of the error, which we already know is mu squared, okay? These results were proven before, okay? So, we know that this term here is trace of GL plus some higher order term of mu, and this term here is mu squared, correct? Okay? So you can see mu squared and mu squared, this will give you a higher order term, right? And mu squared and this mu here will give you another higher order term, right? All these terms will be lumped into the higher order term, right? The same thing will happen here. So what will be left? Will be left mu squared, the trace of G, which is the gamma that you want. The mu squared trace of G plus all higher order terms. So I still need just to show that this last term here is higher order in mu, and we are done, right? No, don't forget, there is a mu squared already there, so, right? So if I can show this is also has some mu in it, then I'm done, correct? So that last term, here it is, okay? This is the last term, right? Okay, it's not difficult. Not difficult, just be patient, okay? Let's condition on the past data first. Why do I condition on the past data? Because, look, I'm taking the expected value of the magnitude, okay? Because that's an inner product, so this is a number. When I condition on the past data, okay, so this quantity here goes outside the expectation, right? You see, the inner product of two vectors, this is less than or equal to the norm of one, norm of the other, correct? That's what I'm saying here, less than or equal, norm of one, norm of the other, correct? But the other is under expectation. The first is not, because it is independent of the data, correct? Because it's conditioned on the data. Well, the first norm, this first norm, okay, is equal to the square root of the norm squared. Nothing changed there, right? Okay, and for the second quantity, right, remember this, that for any number, any real number, any random variable, this is less than or equal to that. Correct? We saw this many times, correct? Okay, therefore, expected value of, let's say A is non-negative, is less than or equal to the square root of that. This is exactly what I wrote in going to that. Expected value of the square, correct? Very good. But this one we already know is some multiple of the fourth power of the error. This is what we showed before, okay? This did not change. But this one now, well, this is what we assume on the noise, that the second power of the noise, the second order moment of the noise is bounded by, right, conditioned on the data, is bounded by the second order, right? Fine, so far, things that we have done, okay? Well, the square root of the sum of two square quantities, right, this is upper bounded by the sum, you unsquare the quantities. They're very easy to check. Just to square this, it's larger than that. Right? If you square this, you get this square plus the cross term, right? Okay, so now multiply them together. What do you get? You get w cubed plus something that depends on w squared, right? This is of the order of mu already, and there was the mu squared, so this will go into the higher order term. What about this? Okay, well, this also, let's look at the mu cubed, okay? So forget about the second term. The second term will give you mu, we already know, because it is mu. What about the first term? Well, we can again use Jensen's inequality. We did this trick many times, right? Because the fourth power is of the order of mu squared. To the power 3 over 4, it becomes 3/2, which is larger than mu, times the mu squared. You understand? Okay, so I was able to show that that last term also, right, is higher order power. Is of the order of mu, because this term here dominates. And then when you multiply by mu squared, it becomes higher order power in mu, and then we are back to what I wanted. Did you follow the argument, right? Okay. Some algebra, but it's not difficult algebra, okay? So I was able to establish this result here, okay? So now, with all of this, now I can develop my adaptive strategy, because remember, what I wanted is to estimate this, right? To estimate this at agent L. Well, agent L already has the W and the psi, right? Estimating that is like estimating 2 times that, doesn't matter, right? So you just run this recursion, this is smoothing filter, right? You understand what I'm saying, right? Because you see, if you take the expected value of both sides in a steady state, expected value of this, you know, this term here, you group them together, you will get zeta times the expected value of this. By the way, there is a typo here, right? Correct? Okay. When you group these two terms together, under expectation, you will get the expected value of gamma squared times the zeta L. That zeta L cancels this zeta L, right? So you see that in steady state, the expected value of gamma of this quantity here, right? Of this quantity here will go to the expected value of this, correct? Therefore, the expected value of this, right, here I have it correctly, okay? So what's the argument here? So the expected, okay, why do I have the over 2 here? Okay, so what I would like to do, I would like to estimate, yeah, okay. Yeah, the notation is a little bit, okay. You see, so the expected value of gamma hat goes to the expected value of this, correct? The expected value of this is 1/2 of the expected value of that, which is the gamma, right? So gamma hat is going to 1/2 of gamma, right? The notation wasn't very, okay, it's a bit confusing, but you get the idea, right? Okay, but it doesn't really matter that this estimate is going to scale the multiple of gamma because you have it in the numerator and the denominator. This scaling will disappear, okay? You understand? Very good. So, okay, so that's it. Once you estimate the gamma, you plug it into your expression for A, and you get an algorithm like this, right? An algorithm like this. Okay, so I say this is agent-centered because this is done at every agent, right? So every agent is doing adaptation and combination, right? So once it does the adaptation, it has this difference. I'm calling it Y. It's smoothing the energy of Y over time, right? Smoothing the energy of Y over time, and then this is the gamma you use for the A, and then you do the combination, right? So you just added these 2 lines here, right? This is just a simplified notation, right? So this is done at agent L. So in this particular implementation, what do the agents have to share with each other? They share the psi for the combination, and they share the gammas, right? Very good. And each agent computes its psi and its gamma. Right? This is agent-centered. There is another way to do this calculation. So here, if you want to reduce the amount of information that you are transmitting, okay, you can ask agents to, here, every agent is doing some calculation and more transmission, right? You can ask them to do more calculation and less transmission. That's just a matter of preference, right? Depends on your application. That's what this other implementation is, okay? I call it neighbor-centered. Let me show you what I mean by that. What I mean is, what you want is the quantity on the left. Agent L can compute it by smoothing, right? But now I want to move the calculation of that to agent K. Agent K cannot compute it because agent K does not know WL. Agent K only receives psi L, right? But agent K has an estimate that's close enough to WK, right? This is just now an intuitive construction, right? So agent, if you want me, agent K, to do this calculation, the best I can do is do something like this. Of course, there are other variations we have been discussing today, right, to improve on this. This is just one idea. Not necessarily the best, but one idea, okay, to get started. So agent K can do this, okay? So this is it. So agent K smooth is this difference. I compare what you sent me with what I have. Okay? And then this quantity will be an approximation for what you want. So if you implement it in this way, okay, okay, you end up with this recursion here. This implementation here. Okay? So now agent L is sending only psi, correct? Just like before. I am agent K, and I have several neighbors L. For each one of my neighbors L, I have to compute this difference and smooth it. So as an agent K, I have to compute several gammas, one for each one of my neighbors, correct? So it's more calculation now, but less transmission, okay? And not only that, if he's my neighbor, I'm computing his gamma, and if he's her neighbor, she's computing his gamma as well. Right? Okay, so the calculations are spread now. Each agent is doing more calculations, and some calculations are redundant, but that's what this implementation does, okay? You understand? Okay? This is all based on the result of that lemma, that if you compute things like this, on average, this quantity will give you what you want, will estimate what you want, okay? Now, you can use ideas like this to solve problems of the following form, and I know one of your groups will be talking more about this during the class project presentations, okay? So, one idea is to do the following, okay? Here I have a mean-square error network, running diffusion LMS, right? I have different agents receiving data from neighbors. All of them have the same model in this example, okay? And each agent K is estimating the gamma of its neighbor, right? And using that to adapt the A, correct? So this is an adaptive implementation, including adaptation of the combination policy, okay? Now, you can use implementations like this to solve problems of the following kind. If you allow the network to adapt the A's, then with time it will end up learning more or less which A's it should emphasize and which A's it should not emphasize. This is the purpose of the clustering algorithm, okay? So this is an illustration here, okay? Why? Because it's comparing your psi to my W. And if that difference is too large or too small, that will reflect on how much weight you are going to get. So okay, so this is one particular way, a simple way, but one particular way of doing clustering. Okay, and also of detecting intruders, because intruders could be someone that is feeding you with wrong information or has the wrong W, or it could just be a node that's malfunctioning. So its psi, whatever psi it's giving you, may not be consistent with your W. Over time you learn that, and the A's may end up become weaker here around it, right? This is one way of applying these constructions, okay? Now, I have some simulations here, okay, over a mean-square error network. Let me go to the curves, okay? So this is for regressors of size 10. I give you the values of the zetas I'm using in this simulation here, okay? A network with 20 agents. This is the noise profile and trace of RU. And this is what I want to show you in this simulation, okay? I just have a mean-square error network with 20 agents, fine? Now, let's look first at, okay, let's look first at the black curve, which is the highest. Here I'm using a static combination policy, which is the uniform policy, right? That's the performance you get. In this particular example, if I use instead the metropolis rule, which is static, it gives me better performance for this example. That's this second curve that you see down here, okay? Now, the other two curves, the blue and red curves, right, these blue and red curves, they use adaptive combination policies, okay? Adaptive combination policies. One is the No, sorry. Yeah. The red curve is using the adaptive combination policy, the one I just showed you, where you estimate the gamma using a smoothing filter. That's the red curve. The blue curve is using the relative variance rule, assuming you know the noise variances. You don't need to estimate them, right? That's the best you can do. So the best you can do is the blue curve, right? And the adaptive curve, you can see it gets close to it, not so close, because now you are adapting additional. You are adapting n or n squared coefficients, right? These are, of course, not n, because if it's generally sparse, you have less than n squared entries in A, but you are adapting many more entries now, right? And you already know from 210A and from 210B that each time you add an adaptation step, you add some mean-square error deviation, some more errors. So that explains the difference. But it is better than the other two, the static solutions, right? Okay, so you see improvement in performance, okay? So in the blue curve, I assume I know the noise variances. In the red curve, I'm learning them. So I do better than the static. But you lose in one respect. The convergence rate is slower, right? The convergence rate, why? Because it takes time for you to learn these quantities, okay? So the convergence rate is slower. Performance is better, but convergence rate is slower, okay? Now, you had a question?
Yes, the adaptive combination rule, is that the one where they're sharing the gammas, or they're only computing the gammas of their neighbors?
No. These ones I'm adapting the gammas. Adapting them using a smoothing filter.
Yes, but you're getting them from your neighbors?
Oh, you mean which one? Which of the?
Yes.
I don't remember. I have to read the text. I don't remember which version I'm using in this simulation.
I'm wondering if you are estimating the gammas of your neighbors, how much is that error?
Yeah, I don't. Okay. Yes. Yeah, I don't remember which one. Please read the text and find out. If not, ask me and I'll look back into my code, okay? Yeah, you're right. So he's asking which version of... Sorry, which one? The first one. Okay, so I'm using the version where each agent estimates its own gamma. It's written there?
Neighbor center.
Oh, neighbor center. So I'm using the version where each agent computes the gamma for all of its neighbors, okay? Fine. Now, how do I improve the convergence? Okay. You see, there is some other work. I'm not going to cover it here, but it's not difficult for you to read it. I give a reference to it in my notes. You can show that. Okay, the best policy for you to use to speed up the convergence of a network, okay, is the uniform policy. Okay. You can show that we have, oops, I have a reference to it somewhere here. Well, if it's not here, it is in my notes, okay? Where is that plot? Okay. So if I use the uniform rule during the initial adaptations stage, okay, the convergence rate will be the fastest it can be. Of course, this is subject to an approximate argument. This is not, right, an exact statement, but a good enough statement, okay? So if you use the uniform rule, you can show that gives you the fastest initial convergence. But you see from the plots, it doesn't give you the best steady-state performance. So what you can do, you can use a strategy that switches, and I have the plot here, switches between the uniform rule and the adaptive rule. Okay, so here, let's look at this plot. Look at the blue curve now. The blue curve is the adaptive combination rule again. So what I do, up to a certain time instant, I think it was up to 1,000, I believe, up to 1,000, I'm training my network with the uniform rule. So you can see the convergence matches the convergence of the blue curve. At 1,000, I switch to the adaptive rule, right? So once you set up the convergence speed at that rate, then it continues moving there and it achieves, okay, you see it achieves the performance of the one that is adapting right from the start, right? You understand?
But in the background, you're estimating gamma.
In the background, yeah, for this one, yes, I'm estimating gamma. Yes, I'm estimating gamma. Yeah, yeah, even before gamma. Yeah, that's what I remember now. Yes, I'm estimating gamma. Otherwise, here you will see a discontinuity. Okay, but to be sure, I have to go back to my code. But I'm almost sure. I may say it in my text also. You can read the text. Maybe it's said in the text, okay? But I'm almost sure that's what I'm doing. Okay? So uniform, and in the background you're estimating gamma, and then you switch. Of course, the question now is when is the best time to switch, right? So in that article, we give one construction that tells you one way to detect when it is the best time to switch, okay? You understand? Of course, I'm not giving you all the answers, but this tells you that there is more to be done, right? But these simulations are showing you that you can't really extract more performance from these networks, okay, than just using a static combination policy, okay? Very good. So I showed you in this lecture how to adapt the combination policies, right? And I showed you that indeed you can gain some performance, okay? So I'm going to conclude here, and next time I'll give you some general remarks, okay, about issues that we haven't discussed in this course, okay?